Did you know that the faster you move, the heavier you get? This is actually explained in Einstein's theory of relativity. Marhaba! This is Mr. Jesse and welcome to another episode of Physics is Easy with Mr. Jesse. This lesson is on Chapter 28, Section 3, the Bohr Model. For this lesson, we will cover the following objectives. First, state the basic assumptions of Bohr's model of hydrogen and derive the energy levels from them. Second, define ground state and ionization energy. We will also relate the energy levels obtained from Bohr's model to the Redbirds Equation, state Bohr's Correspondence Principle, and lastly, to apply Bohr's model to hydrogen and hydrogen-like atoms. At the beginning of the 20th century, it wasn't understood why atoms of a given element emitted and absorbed only certain wavelengths. In 1913, Bohr provided an explanation of the spectra of hydrogen that includes some features of the currently accepted theory. His model of the hydrogen atom included the following basic assumptions that are being discussed on the next slide.
Hello everyone. Today we'll be looking at a little more detail at Bohr's atomic model, which he used to describe the structure of the hydrogen atom. Unfortunately, he couldn't really extend it to bigger atoms, but it was still pretty good. It was the first model to ever use quantum physics. So, without further ado, let's get started. So Bohr's 1912 model used a radical new quantum physics, which was still pretty controversial at the time, to explain spectral lines. So it was the first time quantum physics was ever used with a sort of actual real application other than explaining blackbody radiation. And in fact, the first time it was used to describe particles like electrons instead of just packets of energy. The model consisted of three main postulates, all of which were pretty crazy at the time, but all worked really well together to explain the spectrum of hydrogen. So the first and biggest postulate is that electrons can only occupy certain energy states. They're not just orbiting around a nucleus, but they have to be at certain energies around the nucleus. They can't be anywhere in between. And that's sort of the main quantum physicsy bit. So the electrons around the nucleus do not radiate energy, as classical physics would have them do, but instead they're sort of stuck at each state. They can't move in between. So electrons in different orbits have different energies. So the lowest orbit will have the lowest energy, and it won't be able to spiral inwards, and it won't be able to spiral outwards. It can only jump. So Bohr's second postulate defines what these allowed energy states were. So we have energy level 1, 2, 3, 4, and so on. So the equation he came up with was this one here. mvr, which is the angular momentum of the electron, equals nh over 2 pi. So mvr is the electron's angular momentum. Fairly important. This is sometimes known as the rule of quantized angular momentum. And the integer n on the right side of the equation is called the electron's principal quantum number. It corresponds to the energy level of that electron. We can see that there are a few other letters in here, so I'll just quickly go through them. H is Planck's constant, which you should be familiar with by now. Pi is the circle number, 3.14-ish. And so this means that the energy level, the quantum number of the bottom energy level is 1. And so the angular momentum here will be given by this expression. So this will be h over 2 pi. This will be 2h over 2 pi, and so on and so forth. Now at first the units might look a little odd here, because you think, hang on, integers and constants like pi don't have units, but Planck's constant is in joule seconds. How does that work when angular momentum is given by this equation, which is kilograms meters per second times meters. Well, it turns out that 1 joule is the same as 1 kilogram meter squared per second squared. And so if we multiply this by another second, then it'll match up exactly with this expression here. So that means that although they at first look different, the units on both sides are equivalent, which is pretty important when we are making a new physical law. So Bohr's third postulate, we're still on the postulates, explains the spectral lines of atoms. And this is what allows electrons to jump between energy levels. The postulate says that when electrons change their energy level, they absorb or emit a photon. If they go from a high energy level to a low energy level, they emit a photon of energy. If they go from a low energy level to a high energy level, they can only do it if they first absorb a photon of energy. They sort of make this jump, as you can see. So the energy change is equal to the energy of the photon. It makes sense, right? But you need to write these things down if you're making a whole new theory. So we can see that the change in energy, which is the final energy state minus the initial energy state, will be equal to the energy of the photon, hf. So this was the first model that could successfully describe the spectral lines of hydrogen, which is pretty good because up until that point they were a little bit of a mystery. It was also the first model that used quantum physics to describe some aspects of the atom. Everything before that had been using classical physics. The model still had a number of flaws and problems. It was a big step forward, especially for using quantum physics to model the real world, but it was far from perfect.
Now let's talk about the relevant equations of Bohr's atomic model. The first equation is the radius of the atom, or the radius of the electron's orbit. Now this equation is based on the assumption that the electron can only exist in certain allowed orbits. So he was able to come up with a mathematical formula, and it is this formula over here, where r sub n is the allowable radius, and n is an integer, 1, 2, 3. H bar is just equal to the Planck's constant divided by 2 pi. Ke is the Coulomb's constant, and that is 9 times 10 to the power of 9 Newton meter square per Coulomb square. E is the magnitude of the charge of electron, 1.6 times 10 to the power of negative 19 Coulomb. And Me is the mass of the electron, that is 9.11 times 10 to the power of negative 31 kilograms. Also, I would like to point out that the N here is actually the energy level. So for example, Rn simply corresponds to the radius of each energy level. So for Rn is equal to 1, or when n is equal to 1, the radius, or the orbit has the smallest radius, and this is called the Bohr's radius, or a sub o, and it has a certain value. So if we are going to substitute n here with 1, and then this quantity here is actually a constant, so therefore r sub 1 is equal to the Bohr's radius, and it has this value. Then this tells us that we could express this formula, this general formula, in terms of Rn would be equal to n squared, or the energy level, multiplied by the Bohr's radius, or we could say Rn is equal to n squared multiplied by 0.0529 nanometers. So here is a representation of the radius for each orbit, and it follows the general expression r sub n is equal to n squared multiplied by the Bohr's radius, where n is the energy level. That's the energy level. So if we have here the proton, this is a proton, and we have here the electron, the radius of the first energy level is just equal to the Bohr's radius. Now the radius of the second energy level would be equal to 4 multiplied by the Bohr's radius, and also for the radius of the third energy level, it's going to be equal to 9a sub 0, or 9 multiplied by the Bohr's radius. Another relevant equation that you have to take note for this lesson is the energy of the quantum states. So Niels Bohr was able to come up with a formula that allows him to solve for the energy associated with an electron at a specific energy level n. And it is actually this equation. It looks fancy, but all of these can actually be simplified with a constant. After all of these are constants, so therefore we could express this particular equation as the energy associated at a certain energy level n is equal to negative 13.6 divided by n squared, and this is expressed in electron volt. The negative sign here tells us that the electron is bound with the nucleus, since the nucleus is positive. So electron is bound with the nucleus. So using this equation, we would be able to solve for the energy of the electron when it is on its ground state, or when n is equal to 1. So at ground state, n is equal to 1, and the energy associated at ground state, or the energy of the electron when it is on ground state, is just equal to negative 13.6 divided by n squared, and our n is equal to 1, and this is in electron volts. So therefore the ground state energy is equal to negative 13.6 electron volt. Consequently, the energy of the electron on the second energy level, so we would substitute n to 2, so we will have negative 13.6 divided by 2 square, and this would give us negative 3.4 electron volt. So once again, I would like to stress out that when we talk about ground state, that means n is equal to 1. Now let's talk about the ionization energy. The ionization energy is just the energy needed to completely remove the electron from the atom. So if we're talking about the hydrogen atom having 1 proton and 1 electron orbiting around it on the first energy level, this electron, being on the first energy level, possesses an energy equal to negative 13.6. Again, the negative sign tells us that the electron is attracted with the nucleus. Now, in order for us to liberate this electron over here, it must gain an energy equal to the energy that it possesses in order for us to remove this electron completely from the atom. So therefore, the ionization energy of the hydrogen is 13.6 electron volt, meaning these electron here must receive or must absorb an energy equal to 13.6 in order to completely free this electron from the hydrogen atom. Alright, so with the equation E sub n is equal to negative 13.6 divided by n squared, and this is in electron volt, this tells us that the uppermost level would correspond to E is equal to 0, and that is because n here would approach infinity. So therefore, when you're very, very far from the nucleus of the atom, the farther you are from the nucleus of the atom, the less energy you're going to, or the electron is going to possess. So in fact, in the uppermost energy level, that is n, approaching infinity, the energy at that point is equal to 0. Now let's look into Redbirds equation once again. So whenever a transition occurs between a state Ni to another state Nf, or when electrons move back from a higher energy level Ni to a lower energy level Nf, a photon is emitted. And the energy of this photon is equal to the amount of energy that the electron absorbed in order for it to jump from a lower energy level to a higher energy level. So once again, in order for it to go back to a lower energy level, it has to emit the energy that it has absorbed in a form of a photon. And the wavelengths of these specific photons can be solved using Redbirds equation, which is equal to 1 over lambda is equal to RH, the Redbirds constant, multiplied by 1 over n final squared minus 1 over n initial squared. And this is actually very similar to the previous Redbirds equation, which is this, multiplied by 1 over m squared minus 1 over n squared. It's just that our m here is the n final, or the final energy level, and then the n here is the initial energy level. And for the Paschen series, n final is equal to 3. So we have here, this is actually the final energy level if we talk about Paschen series. For the Balmer series, the final energy level is the second energy level. And for the Lyman series, the final energy level is the first energy level. Now, it is also worth noting that for Paschen series, infrared radiations or the photons are most likely in the infrared radiation, whereas in the Balmer series it's in the visible spectrum and some visible spectrum and UV. Whereas for the Lyman series, it's purely UV. So the photons emitted as electrons move from a higher energy level towards energy level 1, that is for the Lyman series, they are going to emit a photon in the UV spectrum. One of the objectives for this lesson is for you to be able to state Bohr's correspondence principle. Here is the statement. Bohr's corresponding principle states that quantum mechanics is in agreement with classical physics when the energy difference between quantized levels are very small. This is particularly useful in predicting the wavelength of the photon that will be emitted by an electron as it moves from a higher energy level to a lower energy level. Now, this equation would be true if your initial energy level is close to the final energy level. So we'd say, for example, n final is equal to 2 and n initial is equal to 4. So they are relatively close to each other. However, when your initial energy level is very, very big compared to your final energy level, the Redbirds equation may not be able to accurately predict the wavelength of the photon that the electron is going to emit, and therefore quantum physics is no longer in agreement with classical physics. The analysis used in the Bohr theory is also successful when applied to hydrogen-like atoms. Now, an atom is said to be hydrogen-like when it only has one electron. So examples of that would be a singly ionized helium, so He positive 1, or a doubly ionized lithium, so that would be Li positive 2, or a triply ionized beryllium, Be positive 3. So all of these would contain one electron and therefore may be treated as hydrogen-like. Now, to solve for the energy associated with the energy levels in hydrogen-like atoms, we have this equation, and it is very similar to the energy in each quantized state in a hydrogen atom, which can be solved using the equation En is equal to negative 13.6 divided by n squared, and this one here is electron volts. So the only difference for hydrogen-like atoms is the inclusion of the atomic number Z. Also, the wavelength of the photon that will be emitted by the electrons of hydrogen-like atoms can be solved using this equation, and this is very similar to the wavelength of the photon that is emitted by a hydrogen atom, which is actually this equation. Let me just write it down. Minus 1 over Ni squared. And the only difference, again, is just the presence of the atomic number. There are other relevant equations that are involved in Bohr's model of the atom, and these equations can be found in WebAssign. So on WebAssign, I included a tutorial exercise that shows you how to solve for the linear momentum of the electron, the angular momentum of the electron, the kinetic energy of the electron, and the potential energy of the electron. So make sure that as you do this tutorial exercise, you are going to take note of the relevant equations. And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.